Now, I mean, technically I did get a full recording, but part of it was kind of crooked and only got half the screen. So we'll try. All right, let's start the party. So for people who did that on, well, I guess that's everybody, but among the people that did the on the wire thing, who got the most levels for logging into different Linux things? We did that a couple weeks ago. You got level 9? Okay. Anybody higher than 9? Mitchell. Pardon? 15. Can anybody beat 15? No? Okay. Well, oops, hold on. I gotta get something else. I guess. All right, so first of all, as a person who solves puzzles, here's more puzzles for you to solve. I got you a book for crossword puzzles. And then we also have special awards related to the IS 404 class. So this is a sticker that's limited edition. You can only get this if you do something special in here. So these 2 items are going to you. Let's give them a hand. And just on a side note, a bunch of our students at the Silicon Slopes event, they waited in line to get skateboard decks from one of the vendors, and then Jocelyn Bunderson gifted hers to me. So I just wanted to show it off. I think that's totally awesome. And then just for Brandon, who always encourages me to, work on my ollies and stuff. Trying to Yes. Okay. I'm not very good at it, but that's an attempt anyway. Okay, so everybody's alive now. So anything class business-wise that you want to ask about or talk about before we move into things? Yes? Oh, see, I didn't want to tell you that on purpose. I didn't want to bring you down. So, level 19. The guy sitting right there, it was Eric Lewis. So now you know who to go get,
I already did all of them before.
So, well, the next question was, okay, how long did it take you? So how long did it take you?
A couple hours.
Okay, yeah, he's like, well, yeah, 1.5 to 2 hours was his answer. So he did not admit whether or not he cheated. I assume that he didn't, but who can say? Other things. Anything else you want to talk about? Life, universe, and everything. Nothing? Yeah. Oh, yeah. When's your half marathon coming up?
It's a full marathon on Saturday.
Oh, full marathon this Saturday, and where's it going to be?
Phoenix.
All right. Well, good luck on that.
I'll be peacing out during machine learning tomorrow. So, yeah.
Awesome. All right. What was your other question? Pardon?
No, there was no question.
There was no question. Okay.
You
All
just
right.
asked for updates.
But I was thinking about that earlier. I was like, oh yeah, he's doing his run soon. Well, good luck. I'm sure you'll do much faster than I would do. So. Okay. I'm really excited about the routing activity that we're going to get to later today. We'll see how the rest of this goes. So we're going to get through the IP information first. Last class, somebody asked about this point, when do we have an exam? I think it says in the syllabus around February 24th, or anyway, it's near the end of the month. So it's almost like you have a whole month. So don't worry about it.
It took 2 weeks.
Okay. Layer 3, we talked about, so just reviewing real quickly until we get to where we got last time. We talked about each computer has a MAC address. They also have an IP address. And the MAC addresses are kind of like devices or a network card's DNA. It's a unique identifier. But the IP addresses are reassignable. There are certain ranges within which IP address numbers can fall, as we talk about the 4 different numbers that make up an IP address. Talked about the background of IP addresses, how it relates to military communication. And so we want redundant paths, and Morpheus would approve of the internet as currently designed. It's all okay. And lastly, we started talking, well, almost lastly, we started talking about the difference between private and public networks. There are different addressing schemes associated with those, and so if an address falls within these ranges, it is a private address. If it falls within these ranges, it is a public address. We're going to revisit some of those other facts about them in just a little while. We did some pinging of places like Google and BYU, and through that, we can use that as a kind of like a diagnostic tool to find out, A, if we're connected to the internet, but B, we can find out what the IP address is associated with a given website. And then I had you talk about this for a little bit. One thing I would like to emphasize for a moment here is consider the ovals here to be like neighborhoods. I mean, granted, this is a floor of a building, but think of it more like a general location within which there's lots of something. Over here, whenever we see a 0 in the context of this class that ends a network address, that is technically a network and not a host address. So within this neighborhood, which we call a network that ends in a 0, we have lots of individual IP addresses, 1, 2, 3, 4. Within this neighborhood, which ends in a 0, we have 10, and then starts with 10, and then it ends with like 1, 49, 97, etc. So we're going to talk more about that idea a little bit later, but that's a good idea to plant in your head as a seed right now, that within a given area, there's this idea of a network. And so I had to talk about it. All right, so I'm going to then reinforce some other ideas and add to it a little bit. We could also consider a MAC address to be like a social security number. If somebody is in the presence of their social security number, my first question would be, can you use that to uniquely identify a person in a room? I see a lot of nodding heads. Well done. I'll mention that in section 1, they really weren't sure about that one. They're like, no. Yes. The answer is yes. So well done, section 2. Okay. Now another question is, could you use this number, if a person has this number on them, could you use that to instantly find out where they are and locate them in the world? No. No, you couldn't. Okay, but a phone number, could you use a phone number to find someone instantly anywhere in the world? Answer is yes. So an IP address is kind of like that. Even though the person that has a particular phone number might give it to somebody else from time to time, you can use it to instantly find somebody. So if I play with that idea a little bit, if I consider a local area network, all of the devices here have MAC addresses associated with them. And in terms of the switch and the devices in here, those MAC addresses are very important. They all get to know each other well this way and differentiate one another. But if you cross over the router into the broad internet and somebody sees that MAC address out there, does that have any meaning to anybody out there or any devices out there on the internet? Hopefully I'm asking that question well. Like, does that MAC address, if it's out there in the wild on the internet, does it have any usefulness or utility? No, you couldn't find anybody with that. I mean, that only matters if you're on the local area network, so it's kind of meaningless. So we do need our IP addresses in order to find people if we're outside of our little local area network. All right, and I'll just let you read this one. So in some ways, this sounds similar to what happens at layer 2 with our Ethernet frames, but we're definitely expanding where we can be sending and receiving our packets rather than just on a local area network. All right, and so we saw this last time, the idea that for any IPv4 address, we get 4 numbers associated with it that are roughly between 0 and 255. And we read it like this for convenience, but in terms of the computer reads it as 32 ones and zeros. So it's also called a 32-bit address. All right, and I had you check and see which are valid numbers and which are not valid numbers. Let me go on to the next activity then, which is, this is good practice, because you're gonna, when we get into subnetting in a future day, you're gonna wanna be really good at this. So, here's an IP address for BYU, one of their IP addresses. By hand, turn it into binary. What is our first step in solving these kinds of problems? Write 1 through 128, exactly what you said.
Yes, that's what I said, yeah.
So. And by all means, feel free to talk to one another. Okay, so when we start with the number, we work from left to right and start subtracting that from whatever the number is that we want to get to. So, how many 128s are there in 128? One, so we do 128, and then we're left with nothing. So the binary for this is 1 followed by 1, 2, 3, 4, 5, 6, 7 zeros. Okay, sadly the next one is a little bit harder. So is there a 128 in 187? Yes. All right, so I'll come over here and I'll type in I'll write in 128. So I got 59 left. Okay, is there 64 within 59? No, can't use that. Is there a 32 within there? Yeah. Yep, okay. 2, so I got 7 and 2. All right, so is there a 16 within 27? Yes, all right, 16. So now we've got an 11. Is there an 8 within 11? Yes. So now we've got 3 left. Is there a 4 within there? No. All right, and then there's going to be a 2, and there's going to be a 1. So there's our binary for that. And then for our last one here, is there, so we'll kind of try and do this a little bit in our head. Actually, this is going to be easy. So we'll just go 0, 0, 0. Hey, there's a 16. 1, 0, 0, 0, 0. Okay, I like that. All right, we'll get more practice with that in the future.
What about 100?
What about 100? I haven't worked that one out today. What if I mess up? All right. So, all right. So is there a 128 and 100? No. How about 64? Yeah. Okay, 100 minus 64 is what? 36. All right, 36. All right, so 1. Is there a 32 in there? Yeah. Okay, so now we're down to 4.
No 16.
All right, no 16. Is there an 8?
No.
Is there a 4? Yeah. All right. And then we're all done. There's nothing left. There's nothing else to take. No. Okay, you did it. Well done. All right. All right, we're going to jump into Wireshark. We're going to jump into Wireshark a couple times now, so if you want to have that ready. Okay, so let's look at an IP packet and its addressing within Wireshark. Okay, I already have mine open. If you are going from the command line, one nice way to open it is to, sorry, this is a little small. No, Control-Shift++. Yeah. You could do sudo Wireshark, and that would open it up for you. You click on the one of the little icons that show the Ethernet graph going, so it's picking up traffic, kind of like a heartbeat monitor. When you click on that, it'll start recording, and then you want to hit stop as it's recording. I've done that previously. So I've got a capture going on. So if I just randomly, yes sir?
What was the command to get Wireshark?
Sudo Wireshark, if you've already installed it. So let me type it in here. Sudo Wireshark. And then it should open up a second version of that for me.
Is that actually pronounced sudo?
Yeah. So I always thought it was sudo, but I watch different videos of nerdy things in the morning while I'm on an exercise bike at the gym. And so I hear people from Australia and England and all places in the world. Anyway, so they tell me that it stands for super user do. So sudo is acceptable.
Acceptable, not correct.
Well, I think it's correct. I think maybe us Americans just assume that it's pseudo, but I'm not sure. It's one of those unimportant things we can argue about.
No, I think you see this has to be in English, and in American English, it says color with an O and not an OU. So clearly the American version is correct.
Could be. Okay, Rowan.
Is Wireshark picking up the whole network or just from your computer to the network?
Okay, Rowan's asking, are we picking up just my computer or the whole network? There's technically a setting on here that sounds like an honor code violation. It's called Promiscuous Mode. And if you enable Promiscuous Mode, then it will be listening to all the traffic on the network. But otherwise, it's just going to be listening to traffic destined for your particular car. Yeah. So you see the little heartbeat line going across your network interfaces, and so just double click on one of them, and you'll see traffic going on by, then you hit stop. So I'm going to hit stop. Okay, and I'm going to select one of these items that has some IP addresses in there. So this is a packet. I see so in the first area, I see its source IP address and the destination IP address. That's a little weird. Anyway, so if I look down in this summary area right here, it shows me the packets as understood by the different layers of the OSI model. The first two we could just kind of group together, our frames and our Ethernet. The third one is the one I care about right now. So as I click on its summary information, I see on that line 192.168.1.1 as the source, and I see what the destination is, and it matches what I'm seeing up there. If I open this up and I scroll down a little bit to some of the other details of this packet header, near the end of it, there's a separate entry for what the source is, and also for the destination. And if I highlight either one of those, it highlights a series of 32 bits in the binary. Any guess what that binary represents? It represents the address you just clicked on. So yeah, look at that one. That looks like a 1. That looks like a 0. That looks like a 0. And that one happens to be 192. All right, fun stuff. We'll come back to this in a minute. Wait, what?
You might have already covered this. How did you get used to the binary? You must be like that B8.
Yeah, so you can just right-click in here, right-click in that box, and it says show the bytes as hexadecimal or as bits. And so you can go back and forth. And then if there's another option here, it says show the text based on the packet. And that's actually referring to this part over here. So if we're looking at a packet from a web page, we can actually see the HTML being put out right there. And we'll do that in just a second. Other questions? Right. We'll be back. All right, next item. This I don't believe is a real map of the routers, but it's representative of what the routers in the United States might look like if each one of them were a red dot. And we know that if we want to get a packet from someplace like Google over to BYU, we have to traverse a bunch of red dots, each having their own IP address. So we go from hop to hop to hop to hop and get to someplace like Google, and then it is going to send our packets back to our IP address by going through each router, hop to hop to hop to hop. And there happens to be a program that allows us to see routers and each of the hops. Now, because of reasons like security, we don't get to see all of the hops, but it's still pretty cool. So, one thing we could do is, let me pick a good window here. All right, so if you're on a Unix compatible machine, the command is going to be traceroute, all one word. And if you're on a PC, you could also do this from a PC, and it would be traceRT, which also stands for traceroute. And so if I type in traceroute, and I can do something like Google, for example. So from my home computer to Google, and my home computer is going through Google Fiber. So Google is my internet provider. Oh, interesting. So what do I see there? I see that it went through 1, 2, 3, 4, 5, 6, 7, 8, 9 routers to go from my Raspberry Pi to the actual Google servers. I can see the address of every single router. So this is the one at my house, followed by one at the internet service provider, another one at the internet service provider, another one at the internet service provider, because they all say something about Google in them. And then it goes bouncing around on some other IP addresses on the internet, and supposedly this would actually be google.com or the last router in front of google.com. Yay! Okay, one of the cool things about doing the Traceroute program is, in addition to the IP address, there's oftentimes a domain name that's associated with that router's IP address. And these domain names give us insight into the router itself. So as I read through several of these that say Google Fiber, that says, oh hey, that's a router that happens to be within the Google Fiber network of routers. Let me do another one. So many of you have BYU domains through the BYU Domains service. That is owned by Reclaim Hosting. We outsource that as BYU to them, so they're not us. BYU doesn't really host it, somebody else hosts it. And let's find out. And so I have a website hosted there, and so my blog is with Reclaim Hosting and through BYU Domains. Oops, Control C, make that stop. So here is the IP address, 192.81.211.144. All right, so that's their address that I've heard is in the East Coast. Now let's see about the routers that we have to traverse in order to get traffic to and from there. So I'll type in Traceroute, and you can do this with any site that you're interested in. But I'll do Traceroute to there. Okay, and it went through how many hops? 17. And as I look through this, I can see that as I leave here, or from my home Raspberry Pi, same path, I'm going through some routers in my Google Fiber network, and then more routers in the Google Fiber network. Oh, it's interesting.
Question.
Yes?
What does the *** mean?
It just means that it can't return an entry for some reason.
Okay, because I'm still doing the Google one, and I'm like 24 in, and the last 10 have just been ****. So I was like,
Yeah, that'll happen sometimes.
Is it a privacy issue, or why is it?
I believe that sometimes they like to hide it. So I'll do the same thing here. So I'll do like Traceroute, so the same thing you might be doing. So this is from my computer here in the classroom. And as I try to go to byu.edu from the classroom, so wherever their website is hosted, the first thing that happens is it goes through a series of routers that are here on the BYU campus, and you can see, based on the domain name associated with that, they're declaring themselves as part of this network. And then eventually, it'll make it out to Google. But yeah, sometimes I don't have a definitive answer. I think it's for security reasons that sometimes it's hidden. But anyway, at any rate, it's just not readable for some reason. I bet you it was probably more readable back in the day, but exposing your IP address to administrative tools probably opens you up to security issues. So let's just say, for example, there are 3 routers that are the main routers coming into New York in the financial district. Well, then if I'm a foreign government, I'm like, sweet, let's spin up 100,000, 1 million computers, and let's just all start attacking those 3 IP addresses and see if we can swamp them. So it's not a bad idea in the modern era, given cyber warfare, to obfuscate your address and not show it. Yeah?
So is it like depending on how many routers it has to go through, that's how long it will take to get the packet back to you?
Okay, yeah, and so we also see off to the right here some numbers related to how long it takes to go from router to router. So there's a calculation related to these. I don't know if these are 3 separate measurements or if like the first one's an average and then things like that. Bless you. But so there's a good question as it relates to routing. So I'm going to maybe change your question a little bit. Does going through more routers means it takes longer than going through fewer routers? What do you think?
Does it like depend on the distance?
That's the best answer for everything in right. It depends. So it depends on a variety of things. Like, yeah, what's the distance it's going over? What's the latency? So it might be a shorter distance, but it might have a lot more traffic going on it. And so the routers themselves are supposed to be listening to all their connections and seeing how far things are away and how long it takes to get responses over a particular line, and then make good choices of where to send things. So This is all the magic of routing. All right, so eventually, for reclaim, so at the very end there, we see as I did a trace route to my domain name, it eventually got to an IP address that was associated with byu5.reclaimhosting.com. Yay! And I also got to see something else, NYIX. So that probably means something as well, if I were to look up what that stands for. Some company or service provider, telecom provider out there. So fun stuff that we can see. All right. Any other questions about that? All right, just keep up your enthusiasm. We're going to play a game in a while. So just hold on. All right, so we've been talking a lot about public and private IP addresses. And a question I would throw out there is, why is it that we have private IP address schemes that are repeated over and over and over again? Like right now, somebody in this room might have this address, as well as tens of millions of other people on local area networks around the world. And why is it there's a public internet address space that has unique addresses that are not repeated, that are unique beacons within the internet? Why is that the case, that we repeat some numbers but not others? Well, here's a graph of what's happened related to the public IPv4 addresses. So the IANA pool, so the pool of available addresses, is in red. And at one time, we had lots of addresses, and then we gave them all away. Technically, they're still available because we would give them out in large blocks to organizations like Google Fiber or whatever else, and we'd say, hey, you can use this million, another one, maybe Comcast, you get another million. So we gave the assignment of them, or the ownership of them, away over the course of time. The green line right there says assigned. So the red and the green are associated with one another. So basically, we used them all up. How did we use them all up? Well, this is some good math to be thinking about. So I would ask a question, how many IP addresses are there theoretically possible? For every single bit that you have, you just go 2 to that number, and that's the number that are possible. This will have important implications as we start talking about designing local area networks. So in terms of our 32-bit IP addresses, we go equals 2 to the power of 32. So this is the original number of addresses that were available. So there were 4 billion, a little over 4 billion. I'm sure at one time when we started doing this, people thought, why would we ever need more than 4 billion addresses? But then internet got super popular, and they assigned out most of the big blocks of this to American companies, and other countries got kind of shortchanged on this. So they came up with another scheme that runs in parallel with IPv4, which is IPv6. And I can't remember the exact number, but the implication of IPv6 in terms of numbers of addresses that you can give out is that for every square inch on the face of the planet, you can have about 1 trillion IP addresses associated with it. So roughly speaking, I believe those are the numbers. So in foreign countries, it's not uncommon that they've gone over to IPv6, but here in the United States, we already took all the big blocks and we don't really need that entirely yet, so we're going to keep on using IPv4 for a while. Yeah?
So you said that like the IP address can be the same if it's different LAN networks?
Yes.
So then could the number be like higher than
So within the private address schemes, you can have an address from among any of the 3 groupings, the 3 ranges. So the 10 range, the 192 range, and the 172 range. Yeah.
Is that why when you want to go to a website that's from another country that isn't international, you have to list something? Does that have anything?
No, there's nothing special about international websites. Yeah. Jen?
So you said that like something so the amount of bits that you have is like 2 to the power of how many bits you have, is that the amount of
It's the number of combinations that are possible.
for like IP addresses?
Uh-huh.
That was just clarifying.
Yeah. So, most of our home networks automatically give us a 192.168.1. And they'll say X address. There are and in place of x, we have 8 bits available. So 2 to the power of 8 is how many addresses can typically be assigned to a home network.
Okay, and then just like.
Well, somebody in the room, what's 2 to the 8? 256. Wow, this number keeps coming up. That just happens to be how, put all ones for 8 bits, and yeah, so all this stuff starts to intertwine.
Okay, so business networks have more than 8 bits though, right?
It depends. It depends. So as an individual, you get to choose whether you want a local area address scheme that gives you 256, 65,536, or 16 million and change. How many do you think you need? So we'll talk more about that. There's another question, Elaine.
So wait, who are the people that were like deciding who gets all the IP addresses, and was this like monetized at all?
I believe there's a corporation and there's a whole story assigned to handle this, and there's a story about it in the chapter. So, yeah, sorry, I don't remember all the details off the top of my head. But just, yeah, certainly it was American-centric, and then it became kind of a public good, and so then we work with other governments and share our blocks and blah, blah, blah. So that's how that happened. All right, other questions? Right, moving on. Okay, we'll talk about this again in a sec. All right, so actually, we'll just review this for a second. What are the private IP address ranges and what are the public IP address ranges? Okay, it's burned into your memories.
Wait, I have a question on that.
Okay.
So, I noticed that my IP address for my Pi and yours was the same. And I'm looking at it
The
now.
absolute same?
Yeah.
Oh, that's crazy. Okay.
Is that just because like they're both private IP addresses to the same kind of router?
Yep. Well, I mean, yeah, basically, I mean, most of our home routers are going to give us a 192.168.1.something address.
Yeah.
So there's a real high likely, yeah, so we're always reusing the same local addresses. Okay, so here's a question. Which of these are private addresses and which of these are public? And feel free to discuss with your neighbor.
Some 172s are 172.32 above. But they're not ours. 11.26.
All right, the reveal.
This is good.
So the reds are the private. Yeah.
Why is that 192 that's like the fourth one, not private?
Because it's 192.168 is where,
Oh, okay.
yeah. And you bet that I did that on purpose, by the way. I knew that it would be tricky, so that's why I put it there. All right, so any other questions about those addresses? These will make great questions for exams, not too hard. In terms of remembering this, these are kind of mutually exclusive here, what's public versus what's private. And I just remember this. it ends up being not too burdensome over the course of your life because you see these same addresses over and over and over and over again. So maybe the first time through you're like, oh, I can never remember this, but then you see it everywhere once you start getting used to it, and you're like, now I can't forget. So, on a campus like this, we're on the on a 10.0 range. This actually gives us 16 million possible addresses on campus, and this one is typically what you get at home. And if we do like 168.1. something, then we usually get 255 possible devices on a home network. We'll talk hopefully more about that at some point. All right, let's see if there's some other fun facts that we should say about, well, yeah, we'll talk about it now real quick. Okay, so other fun facts about our private IP addresses. So we can just kind of contrast based on the words that are there. Private IP addresses are not recognized over the internet. If a router on the public internet sees one of those addresses, it will completely ignore it. It knows by rule, I don't talk to you. Private IP addresses, you assign them as a local area administrator. Public IP addresses are not controlled by you, they're controlled by that corporation that we were just talking about. Who's allowed to get them and who can't get them. Private IP addresses are in your LAN, and they're only usable there. Public IP addresses are used globally and unique. The private IP addresses are repeated over and over and over again on different LANs. A private IP is free of charge. You just plug in a router and you get one. A public IP address you have to pay for. So if a block of public IP addresses is given out to somebody like Comcast or Google Fiber, then that means that if you have your Raspberry Pi plugged in at home, you can just make a request to your ISP and say, hey, for $5 or $10 a month, can you give me a fixed and permanent IP address? And they have one to give to you. And then you could associate that with the domain name, and now you're running a website. You can run as many websites as you want out of your house. They are happy to lease you an IP address because that's what they're in the business of doing, is making money leasing those out to you. All right. Previously we talked about the Ethernet frame. Let's see if I can get my mouse up here. Okay, so with the Ethernet frame, we had a destination address, a source address, some data, and some checksum. Let us look at the second thing that's here. So within our Ethernet frame, there'll be something in there that says, oh, this is an IP packet or something else that's contained in the data area. So if it happens to be an IP packet that's in there, the IP packet looks in part like this. If you remember in your book, there's actually a lot of other headers that can go into an IP packet, but we really don't care about all of them. The things we care about are what's the source IP address of the packet, what's the destination IP address of the packet. Similar to the frame, the IP packet has its own checksum, so some simple math that even a middle schooler could do if you just show them what to do with the series of ones and zeros. You can see how, along with the packet, is how big the packet is supposed to be. So this is just what we want to keep in mind for just a moment. That we have so it's very parallel to this other idea, that we have a source address and a destination address and some data and a checksum. As a side note, but not something you need to know right at this second, but assuming that this data was something like a web page, and perhaps a web page split across multiple packets, then in our TCP segment, we get something like our sequence. So we get a set of numbers saying this is packet 1 and this is packet 2. We put them back together, and then the application has a web page. Yay! Okay. Let us look at again at a Wireshark capture related to visiting a web page. There's some cool stuff in there. Oops, come back, mouse. Okay, so I have Wireshark open currently. I also have a web browser open. If you go to that little globe icon, you can open up your own, I'll just close it. You can open up your own web browser. Chromium. Okay, so oftentimes when we're doing captures, you have to do things really quick in sequence, so you're not capturing things that you don't want. I'm going to go over here and, well, I'm going to prepare for this. I'm going to type in, but I'm not going to hit return, the blog that I want to go to. All right, so ready to go, but I haven't hit return yet. I'm going to go over to here. I'm going to clear out some of the information that's here. All right, I'm going to start my capture. Ready, set. Do I want to save? No. Continue without saving. All right, so it's capturing information. I come over here. I hit return. It brings up a web page. It's done bringing up that web page. Come back over here, and I say stop. Okay, so I've already picked up 1,500 packets, not all of which I actually care about, but I'm pretty sure the green ones I do. Okay, so it just so happens that when it's doing HTML-related traffic, HTTP-related traffic, it highlights the row in green. There's probably some other significance of the colors, but that's just something I've noticed recently. So I want to look at the conversation that's happening, and I want to ignore all the other conversations that are happening from my device to other places. So I'm going to select this one right here. So it's coming from, I already know that this is my personal IP address, 192.168.1.248, and then 192.81.211.144. If I do ping datingkettles.com, that's the IP address I get back from that. So I know that I'm talking to the right place. I know I'm looking at the right packet. Okay. Now I want to filter this. I don't want all 1,500 and some packets. So I'm going to right-click on this, and I can apply a filter, and what I want is a conversation. So I want the packets coming to me and the packets going away from me. So I go conversation filter, and then I'm going to go IPv4. All right, now there's a filter up in that bar right there, and I only, kind of like a game of ping pong or tennis, I only see the messages that are going back and forth between those two IP addresses. And we'll talk about this later, but there's something special about the first three packets there. This is SYN, this is SYNAC, and this is ACK. This is called the TCP IP Three-Way Handshake. It's a setup that happens before you establish a TCP IP connection with someplace. In this case, it needed to set up a connection before it started delivering the web page. The third item here is a GET request. So the source of that is my device, and the destination is the remote server. This is a summary. It says it's a GET request. Later on in this class, we will look more closely at GET requests. So a GET request is associated with something you type into your URL. Usually you just type in something like Google, but whenever you type that, your browser actually appends some additional information. And that additional information is shown right here. So it says like, so it gives a special command, and then it gives other information like what's my browser type, can my browser accept encrypted encrypted or compressed messages, and all kinds of other pieces of information. It might even it'll also tell maybe the operating systems that's making the request, all as part of that. But at any rate, we get the general idea, source request, and if I go down a little bit farther, this is one of the packets that contains some HTML in it. So if we interpret the ones and zeros, it gets turned into this. We can see some HTML tags, something about viewport right there. So if we looked at all the packets, then eventually we would get all the HTML associated with our web page. Okay. If there's no questions, then the last thing to say about this is, why do I care about IP addresses? There's a lot of reasons, but here's about 4 of them. One is, as a local area administrator, you need to make choices about what IP addresses you're going to sign out. Second, as you run public services like a website or a mail server, they're typically reached by some public name like datingkettles.com or mail.byu.edu. And because you can switch out your IP addresses, sometimes you leave things dangling where you're sending traffic to some IP address, but you've moved away from that IP address. Like if this were the real world, you're sending like letters to some place that you don't live anymore. So you do have to watch for that. Things break on the internet when that happens. This week I was also talking with over the last 2 weeks with a student who was migrating websites from one server to another, and it wasn't working. And one of the reasons why it wasn't working is because in the Apache configuration file, when it was installed, it picked up the public IP address it was running on. And so when they just simply ported that over to another computer that had a different IP address, there was a configuration issue, and the Apache wasn't starting up and running properly. So anyway, there's other reasons beyond that. Let's get on to the game. That's what we care about. Yes. Okay, exactly. Even though it's a game, this is all how we feel, right? Want to win. Okay. Okay, so just a fair warning real quick. As I introduce this, you don't have to know anything in the following slides for exams. This is just to kind of get your juices flowing.